Welcome to the Maths Department at Ashton Sixth Form College. We are a team of 8 highly experienced teachers who strive to inspire, enthuse and support students wishing to take maths to the next level. So here at Ashton we offer 3 options to take maths beyond GCSE. Our most popular course is A-Level Maths. This course is for those algebra lovers who are strong at GCSE maths and wish to continue that journey with an A-Level which will support countless degrees and pathways beyond A-Level. Further Maths is the equivalent of 2 A-Levels and is for those very strong students who love maths more than their friends and families, and those who are considering taking maths and science beyond A-Level. Core Maths is equivalent to half an A-Level. This is for anyone with a grade 4 pass in maths who does not want to do A-Level maths but would like to keep their hand in the game and learn how maths can be applied practically to areas such as insurance, investment, probability and statistical analysis. A-Level Maths is a linear course with 3 2-hour exams at the end of the second year. The course is split into 3 sections. So you've got Core Maths, which focuses on the pure side of maths, things like algebra and trigonometry, and Mechanics, which involves forces, tension, gravity, how particles move under certain conditions, and Statistics, which involves probability and statistical distributions and analysis. Core makes up about 2/3 of the course and the Mechanics and Statistics are about 1/6 each. You will study Mechanics and Statistics in both Year 1 and Year 2 of the course. There will be 4 lessons a week and extra support sessions will also be offered. The weekly homework will be an online homework and you will have additional written homework every fortnight. All the resources will be accessible online, so the course textbooks and solutions and work through examples, they can be accessed really easy on your mobile phone.
Further Maths is a second A-Level that is taken alongside your A-Level Maths. It is a linear course which at the end of 2 years you will have 4 or 5 1.5-hour exams depending on modules that you choose to take. The content of the course is similar to the maths course, but obviously we extend it into some really exciting areas of maths. 50% of the course is core, which carries on from the core that you do within your maths course, but taking it obviously to another level. We then choose 2 of the following applied units, but there is an option to take all 3 of these. Mechanics is all about the physics of maths, the forces, the motions, gravity, all those type of things. Statistics, here we just use distributions and we look at how we can model distributions to real life to predict what might happen. Decision, this is a new area of maths that you won't have seen. It's really about how computers use maths to solve algorithms. If we think about a sat-nav, how does a sat-nav know the shortest distance between 2 points? What's happening there? What algorithm is it using? And we'll look at lots of different areas like that. If you sign up for Further Maths, it will be 2 out of your 3 A-Levels. For some people, they can take this as a 4th option. You will have 8 lessons a week because obviously we're delivering 2 A-Levels within this time. Please click through the next few slides and have a look at some of the exciting areas of maths that you would study if you chose to take Further Maths.
Really important that you have a decent calculator and we highly recommend this Casio FX 991EX, the Class Whiz. Okay, take a screenshot of that if you want. You'll be able to find that pretty easily on Amazon, perhaps even places like WH Smith as well might sell this, or your local supermarket if it's a large one. Have a go at this task, which brings together some key ideas about quadratic equations and graphs that you will need for A-Level Maths. The answers will follow on the following slide. Then see how we could apply some of these ideas to a real world problem involving a basketball as you click through the subsequent slides. Okay, I'm going to show you my solutions. You might have something completely different, which still might be equally as valid. So normally we think of quadratic equations as written as ax squared plus bx plus c equals 0. But that's not always the best way of writing one from scratch if you've got certain conditions you want to meet. So if we start in the middle, we want our equation to have equal roots, repeated roots. So you can do that by having a bracket that's repeated. For instance, x plus 2 squared. Now the reason I've done that, x plus 2 squared with x equals minus 2 being the repeated root, is because I'm going to get plus 4 when I expand that bracket. It says I want my y-intercept to be minus 4, so I've stuck a minus sign in front of that bracket so that when it gets expanded, everything will be negative, and we'll have a y-intercept at minus 4, and we'll have our two solutions, x minus 2, repeated. So if we just go down into the box underneath, what we could do is simply take away that minus sign, and we're going to have the same equal roots, minus 2, but the actual intercept is now going to be plus 4, because if you expand that, you're going to get x squared plus 4x plus 4. So if we go to the right now, something that's got equal roots but doesn't have a y-intercept at minus 4, well, I'm going to write a completely different equation. I'm going to write x squared minus 6x plus 9 equals 0. That's the usual form that we see quadratic equations, and the reason why that is going to be have a repeated roots is because it could be written like this: x minus 3 times by x minus 3, with x equals 3 being the repeated root. But notice that this one is going to cut the y, or is going to meet the y-axis at 9, not minus 4. If we go up into the box above, then this is exactly the same as the equation that we've got in the centre. It's just been fully expanded so that now it's in the normal form that we get quadratic equations into, that ax squared plus bx plus c. And it's going to have that repeated root of minus 2, and it's going to have the y-intercept at minus 4. You can just see that from the way that the equation's written down. So if we go into the top box, again, I've written the usual format of the equation: x squared plus 3x minus 4 equals 0. The y-intercept is clearly minus 4, we can see it because that's the way it's been set out as our c. And the reason why we know this is going to have this needs to not have repeated roots is, well, we could show you a different way of writing that. Would be x minus 1, x plus 4. If we expand that bracket, that's what we will get. We'll get our two different roots as being x equals 1 and x equals minus 4. If we go to the left, then I'm just going to take that exact same equation and I'm just going to rearrange it by adding 4 to both sides, taking away 3x from both sides. You can see we've got exactly the same as equation we had a second ago, except this time it's not written in the form ax squared plus bx plus c. So for my last box, I am going to write a totally different equation. It's got to be in that form. So it's not going to be in the form ax squared plus bx plus c. So this is the easiest way to write a quadratic equation sometimes. I want two different solutions. So just write two brackets next to each other that you know is going to expand to make the quadratic. Our two different solutions would be x equals minus 5 and x equals plus 3. And we can tell that the y-intercept is not going to be minus 4 because when we expand that bracket, we are going to get minus 15 at the end for our c. So it's going to have a y-intercept of minus 15. Okay, so I'm going to draw a line that goes into the hoop. You have probably got something very similar to this green path here going into the hoop. If we were to draw a path that doesn't go into the hoop, you might have something perhaps overshooting the hoop, like this red line here. You might have something going much steeper into the air and then perhaps dropping before the net and not going into the hoop. But I think you can see that we've got two lines that have some similarities. The similarities being the shape of those two lines. They're both making parabolas. Now, if you think about what we were doing in a couple of slides previously, we could actually say these look like quadratic graphs. Another thing we could say about them is that they would be negative functions. So you'd have a minus sign in front of your x squared. If you was to model these on an axis with some coordinates, you might say that they both go through the same point, the origin. If you imagine 0, 0 being above the man's head. Perhaps a difference between the two graphs might be that the green line has a solution at perhaps x equals 3 meters, whereas the red line has a solution at perhaps x equals 5 meters. Okay, so I'm going to draw a path now through those three distinct points that we've got, and I think you'll have something very similar to this red line here. The basketball is not going to go into the hoop unless it bounces off the floor, bounces back up into the air perhaps, and then drops in. Maybe you got it into the hoop that way. Again, we can see the similarities. It's a negative quadratic graph. It's perhaps going to go through the point 0, 0, the origin, if that's where we are having it. The differences might be that it has a maximum at a higher point to any of the other two graphs that I drew anyway. Also, there might be a solution to this of perhaps x equals 2 meters rather than 3 or 5 like I saw in the other graphs that we drew. Now, how we could take this a step further is we could start actually looking at some graphing software and seeing could we actually generate these graphs by writing some equations. So there is a website called Desmos, desmos.com. It's free to use and it's really useful for understanding what these graphs are going to look like and how to draw them. So I've typed in a couple of equations that I think are going to give us similar graphs to the ones we've just been looking at. Okay, so as you can see there, I've got two different graphs, perhaps modelling the path of those basketballs. And then perhaps if we overlaid this onto the photo, we might actually be able to come up with an equation that definitely goes into the hoop. But it's a really useful tool to have a play around with to really get your understanding of how equations can be written to give you certain graphs and what the equation of certain graphs is going to be like. You can also write your equations in different formats so you can see what they would look like, whether you had them factorized or not.